Exoplanets, Methods of Discovery and Potential for Life, Introduction to Exoplanets. Exoplanets, Methods of Discovery and Potential for Life is one of the most important and exciting topics in modern astronomy and astrobiology. Exoplanets, also called extrasolar planets, are planets that orbit stars outside our solar system. Over the past few decades, scientists have moved from theoretical speculation to direct observation, discovering thousands of these distant worlds. This rapid progress has transformed how we understand planetary systems, star formation, and the possibility of life beyond Earth. For beginners, exoplanets answer a simple but powerful question: are we alone in the universe? For professionals, this field connects astrophysics, planetary science, chemistry, and biology into a single research frontier. The study of exoplanets, Methods of Discovery and Potential for Life, combines advanced instruments, precise measurements, and complex models to uncover planets that are often trillions of kilometers away. In this article, we will explore how exoplanets are discovered, what types of planets exist, how scientists evaluate their habitability, and why this research matters for humanity's future. Understanding exoplanets. Exoplanets vary enormously in size, composition, temperature, and orbital behavior. Some are larger than Jupiter, while others are smaller than Earth. Many orbit extremely close to their stars, while others travel in wide, cold orbits. What makes exoplanets scientifically valuable is their diversity. Before their discovery, scientists assumed that planetary systems would resemble our own. Instead, observations revealed surprising configurations, such as massive planets orbiting extremely close to their stars, and systems with multiple planets locked in orbital resonances. The study of exoplanets, Methods of Discovery and Potential for Life, allows scientists to test theories of planet formation and evolution. By comparing exoplanet systems, researchers can understand how common Earth-like planets may be, and whether the conditions for life are rare or widespread. Planet detection methods. Transit detection method. The transit method is the most successful and widely used technique for discovering exoplanets. It works by measuring small dips in a star's brightness when a planet passes in front of it. This temporary decrease in light reveals the presence of a planet. This method provides critical data. Scientists can estimate the planet's size, orbital period, and sometimes atmospheric composition. Space telescopes have used this technique to identify thousands of exoplanets with remarkable precision. For exoplanets, Methods of Discovery and Potential for Life. The transit method is especially valuable because it enables atmospheric analysis. By studying starlight filtered through a planet's atmosphere, researchers can detect gases such as water vapor, carbon dioxide, and methane. Radial velocity method. The radial velocity method detects exoplanets by observing tiny movements in a star caused by the gravitational pull of an orbiting planet. As the star moves slightly toward and away from Earth, its light spectrum shifts. This technique provides information about a planet's mass and orbit. When combined with transit data, scientists can determine the planet's density, revealing whether it is rocky, gaseous, or icy. Radial velocity measurements are fundamental to exoplanets, Methods of Discovery and Potential for Life, because mass and density help determine whether a planet could support liquid water or maintain a stable atmosphere. Direct imaging technique. Direct imaging involves capturing actual pictures of exoplanets by blocking out the overwhelming light of their host stars. This method is technically challenging but extremely powerful. Direct imaging works best for large planets far from their stars. It allows scientists to analyze planetary atmospheres and temperatures without relying on indirect signals. Although less common, direct imaging plays a crucial role in exoplanets. Methods of Discovery and Potential for Life, especially for studying young planetary systems and understanding how planets form over time. Gravitational microlensing. Gravitational microlensing occurs when a star passes in front of another star, magnifying its light due to gravity. If a planet orbits the foreground star, it creates a detectable distortion. This method is unique because it can detect planets at great distances from Earth, even in other regions of the galaxy. It is sensitive to smaller planets and those in wide orbits. Microlensing contributes to exoplanets, Methods of Discovery and Potential for Life, by revealing planets that other techniques cannot detect, helping scientists estimate how common planets are across the Milky Way. Types of exoplanets: gas giant worlds. Gas giants are large planets composed mostly of hydrogen and helium. Many exoplanet gas giants orbit very close to their stars, creating extreme environments with intense heat and strong winds. These planets are not habitable, but they influence the stability of planetary systems. Their gravitational presence can affect the formation and orbits of smaller rocky planets. Understanding gas giants is essential to exoplanets, methods of discovery, and potential for life, because they shape planetary systems where potentially habitable worlds may exist. Rocky Earth-like planets. Rocky exoplanets are composed primarily of metal and silicate materials. These planets are of greatest interest for life research because they resemble Earth in structure. When located in the right orbital region, rocky planets may host liquid water on their surfaces. This makes them prime targets in the search for extraterrestrial life. The detection of Earth-sized rocky planets has significantly advanced exoplanets. Methods of discovery and potential for life, shifting scientific focus toward habitability rather than mere discovery. Ocean and ice worlds. Some exoplanets may be covered entirely by oceans, while others are dominated by ice. These planets challenge traditional definitions of habitability. Subsurface oceans beneath icy crusts could still support life, protected from harsh surface conditions. These environments are studied extensively in astrobiology. Ocean and ice worlds expand the scope of exoplanets, methods of discovery and potential for life, showing that life-friendly conditions may exist in unexpected forms. Habitable zone concept. The habitable zone is the region around a star where temperatures allow liquid water to exist on a planet's surface. This zone depends on the star's size, temperature, and luminosity. Planets within the habitable zone are not guaranteed to support life, but they are considered promising candidates. Atmospheric composition, magnetic fields, and geological activity also play vital roles. The habitable zone is central to exoplanets, methods of discovery and potential for life, guiding observational strategies and mission priorities. Atmospheric analysis. Atmospheric analysis is one of the most powerful tools in exoplanet science. By studying how light interacts with a planet's atmosphere, scientists can detect chemical compounds. Key molecules include oxygen, methane, carbon dioxide, and water vapor. Some combinations may indicate biological processes. Atmospheric research represents the future of exoplanets. Methods of discovery and potential for life, moving beyond detection toward characterization and life assessment. Potential for extraterrestrial life. Life as we know it requires energy, liquid solvents, and complex chemistry. Many exoplanets meet some of these conditions. Scientists remain cautious, focusing on biosignatures rather than direct evidence of organisms. False positives must be ruled out through careful modeling and observation. The search for life is the ultimate goal of exoplanets, methods of discovery and potential for life, redefining humanity's place in the universe. Future of exoplanet research. New telescopes and instruments will dramatically increase detection accuracy and atmospheric analysis capabilities. Scientists aim to study smaller Earth-like planets in greater detail. Artificial intelligence and data modeling are also becoming essential tools. These technologies help process massive datasets and identify subtle patterns. The future of exoplanets, methods of discovery and potential for life lies in interdisciplinary collaboration and technological innovation. Summary: exoplanets have transformed astronomy from a theoretical science into an observational revolution. Through advanced detection methods, scientists have identified thousands of worlds with extraordinary diversity. The study of exoplanets, methods of discovery and potential for life, connects physics, chemistry, and biology in the search for habitable environments beyond Earth. As technology advances, the possibility of discovering life elsewhere becomes increasingly realistic. FAQ: what is an exoplanet? An exoplanet is a planet that orbits a star outside our solar system. How many exoplanets have been discovered? Thousands have been confirmed, with many more candidates awaiting verification. Can exoplanets support life? Some may have conditions suitable for life, but confirmation requires further study. What is the best detection method? The transit method is currently the most productive. Call to action. If you want to stay informed about the latest discoveries in astronomy and the search for life beyond Earth, follow our content, share this article, and explore deeper into the science of exoplanets.